see. There it was. So this counting techniques problem, we worked it out. It was like the Apple computers problem. We wanted to select 3 of them to be Apple computers, or at least 3 to be Apple computers, etc. So what we're going to talk about today is conditional probability. And conditional probability is all about what is the probability that an event occurs given that some other event has already occurred. So let's say given that a person is a smoker, what's the likelihood or what's the probability or percentage of people who have lung cancer given that they are a smoker or something like that? You know, like given that one event occurs might change the outcome of another event occurring. So you might think of this as like, we could say the percentage of people who have lung cancer is relatively small, but given the group of people who smoke, the percentage could be higher. So that's what conditional probability is all about. It's basically like, you could look at this example here. It says A is the event that a person has a disease, B is the event that that the blood test on that person was negative. What's the probability that somebody has a disease given that the blood test was negative? Well, we hope that would be pretty small. But that's just kind of the idea of conditional probability. So we're going to go through conditional probability, Bayes' theorem, and then independence of events after 2.4. So we're basically going to try to finish up 2.4 and 2.5 today. That'll more or less finish chapter 2 for us, and we'll be good to go. So let's see, we have an example here that says we have 2 assembly lines, A1 and A2. A1 produced A components, 2 being defective. A2 produced 10 components with 1 being defective. Now, we select one component randomly. Event A1, the component was selected. What is the probability that a component from line 1 was selected? Well, how many come from line 1? Well, we have 2 plus 6, which is 8 coming from line 1 versus 10 coming from line 2. So in total, we have 18 units or components. So there's 18 total components. So then 8 out of the 18 come from line 1, and 10 out of the 18 come from line 2. What is the probability that the component is defective? Well, 3 defective components versus, let's see, 15 non-defective components. So probability of a defective component is 3 over the total number of components, which is 18. Now, what is the probability that you are defective and you come from line 1? So that's basically A intersect B. What's the probability that you are defective and you come from line 1? So that would be 2 over 18. So that's A intersect B right there. Now, given that you are defective, what's the probability you come from line 1? So that is the number of outcomes in line 1 divided by the number of defective components. So the number of defective components divided by, in line 1, divided by the number of defective components overall. So it basically just reduces the sample space. So conditional probability reduces the sample space. Notice the denominator here only has 3 in our conditional probability. That's effectively, conceptually, what's happening is your sample space is being reduced from the total to just a subset. In this case, in this example right here, probability A given B equals 2/3 is really just looking at the defective components and then trying to figure out what's the probability that it comes from line 1 if it's defective versus the probability it comes from line 2 if it's defective. So it's more likely that you come from line 1 than line 2 if you have a defective component already. So it's more likely to have been produced in line 1. Now, the general definition is that probability of A given B is probability of A intersect B over probability of B. So probability of A intersect B over probability of B. That's your conditional probability formula. And you could write on the side, it's pretty much the same if you do probability of B given A. You'd say probability of A intersect B divided by probability of A. So basically whatever is right here on the right is what you stick down here. And then you take the intersection in the numerator. So whatever's on the right of the straight bar is what you stick in the denominator. So we read this as probability of A given B. So that's how we read that. As long as the probability of B is not 0, then we're good to go. So we can define this conditional probability as long as we don't have an impossible event. It doesn't make sense to say, okay, what's the probability of an event given that something else has already occurred, except it can never occur. So we don't consider B being the empty set. All right, so in general, the probability of A given B is not going to be equal to probability of B given A, so don't mix them up. Make sure you get the formula correct, depending on which one is being considered on the left or the right of the straight bar versus the right of the straight bar. So basically we change our sample space from the whole sample space to be just the set of B. So we say B has already occurred. Of those, what percentage is, satisfying A? All right, and another way you could think about this is basically like the area of A intersect B divided by the area of B itself. So it's really just a percentage of the intersection. How much of the intersection takes up the whole new sample space, I guess you could say. So that's the new interpretation, I guess. All right, so probability of liking cats apparently is 0.5. So half of people seem to like cats and the other half of people seem to not like cats. Now, probability of liking dogs is 0.6. And then the probability of liking cats and dogs is 0.4. Find the probability that you like cats given that you like dogs. So what is the probability that you like cats given that you like dogs? This is the probability that you like cats and you like dogs. So you like cats and dogs. That's a different question than saying, what's the probability that you like cats given that you like dogs? So this is going to be probability of C intersect D divided by probability of D. So probability of C intersect D, we could say is 2/5. Probability of D is 3/5, which is 2/3. And that would be good enough, or you could say 0.67. It just depends on the instructions. But here the instructions are not any more clear as far as decimals, so I just leave it as 2/3, honestly. That's the best answer to leave. So that one's pretty straightforward. It's just a straight computation. I have the probabilities, I have the intersection, I can get the conditional probability directly. So that's the easiest type of example to do for sure. Let's look at another example. I can't see the chat, so if you're chatting, just turn that microphone on and let me know that you have a question because I can't see the chat. Let me just open it up, make sure nobody's posted any questions in the chat. Let's see. A few people can't get on Zoom, like 4. That's a problem. Maybe they're here now. Is everybody here now? Let's see, we got 61 still? 62. I guess it's private unless I share my screen and everybody can see it. So, whoops. Rachel, do you know if the rest of the people can see the screen now? They are not the ones who can't.
Yeah, they can't. They're like messaging in like the
Oh, shucks. Okay. So. Okay, so maybe everybody's in now. Okay, yeah, that's weird. That's weird. I did see that thing that said admit people. I didn't think I had to do that. Okay, I guess we're good to go now. The first 10 minutes you can go back and watch after I share the link. But anyway, we just kind of covered this conditional probability stuff. I'll just give a quick recap. Conditional probability, it's basically like what's the probability that an event A occurs given that event B has already occurred. So there's a nice formula for calculating that. It's the probability of the intersection A intersect B divided by probability of B. So given that B has occurred, what's the probability of A? Which is a different question from saying, given that A has occurred, what's the probability of B? So it's a different question. In general, they're not the same probability. So that's kind of what we're talking about, is this conditional probability. And then we did an example here. We just go straight to what's the probability of C given D? Well, that's probability of C intersect D divided by probability of D. So that's pretty much all we've covered so far. All right, so let's see. Make sure no other questions. Everybody's good. All right, so let's look at another example here. Conditional probability. Probability of A is given as 0.14. Probability of B is given as 0.23. Probability of C is given as 0.37. A intersect B is 0.08. A intersect C is 0.09. B intersect C is 0.13. And A intersect B intersect C is 0.05. So let's say you weren't given like the whole chart right here. I gave you the whole Venn diagram filled in individually. How would you fill in this Venn diagram if you didn't know everything already? Say you just had A, B, and C. What you would do is you would start at the intersection of all of them and you would put 0.005, or sorry, 0.05 right there. And draw A, B, and C. Now, you know in A intersect B that you have 0.08. So that's like A intersect B should be right here. So you should have 0.08, and then A intersect C, you should have 0.09, and B intersect C, you should have 0.13. So let's see, B intersect C would be these two. I have 0.05 here, which means I have 0.08 here, because total they should be 0.13. So these two should add up to be 0.13. Then A intersect B, or sorry, A intersect C would be 0.09. I have 0.05 here. That means this needs to be 0.04. And then same thing here, A intersect B should be 0.08. Well, this is 0.05 already. So then this part without C is 0.03. So you just kind of systematically go through and fill out starting at the middle. That's kind of the best way to do it. And now if you know probability of A is 0.14 and you have how much here? Well, 0.9, 0.12. So that means 0.02 here. So that's now all of A adds up to 0.14. So that'd be how you fill in this diagram if you need to do it by hand, but it was already given directly, so that's nice. So what is the probability of A given C? Well, let's look at probability of A intersect C divided by probability of C. That's our formula. And again, those were given directly. Probability of A intersect C is 0.09. Probability of C is 0.37. We do that, we get 0.2432. So again, a very straightforward example. These are not even word problems. I'm literally just giving you the probabilities directly. You don't even have to pull anything out. All right, part B, a little bit more complicated. What is probability of A given B union C? So probability of A given B union C. It says, hint, define an event D, which is going to be B union C. So let's look at this event here, D equals B union C. So D equals B union C. What is the probability of B union C? Because in my conditional probability, I'm going to need probability of A given B union C. It's going to be probability of A intersect B union C over probability of B union C. So first we need probability of B union C. So probability of B union C is going to be, let's see, add all these numbers together. So basically everything right here. So let's see, what's not in there is going to be 0.51 plus 0.02 and then 1 minus that. So 1 minus 0.02 plus 0.51. So B union C would be everything over here. I just kind of shade it in. This would be B union C. So everything there. So everything that's not in there is 0.51 plus 0.02, and then do 1 minus that. And that will give us probability of B union C. Probability of B union C is going to be 0.47. So that's 0.47. And that's going to be our denominator. So divided by 0.47. Now, what's the probability of A intersect B union C? So probability of A intersect B union C. So what is A intersect B union C? That's this right here in green. So that's going to be 0.08 plus 0.04, which is 0.12. So 0.12. So that is probability of A intersect B union C. Now, what you could have done, let's see, this is the best way. You could have done a distributive law like I talked about in class on Friday, but I think this is actually better to look at it this way. Just say that it's these three. So where does A intersect this red stuff? So that's that intersection. And just add those three probabilities together, we get 0.12. So the numerator is going to be 0.12. That fraction turns out to be 0.255. So that is probability of A given B union C. So any questions so far? Don't forget, just stop me, raise your hand. It's probably a way for me to like automatically admit. Let's see. Okay. Justin. You can either like use your microphone or you can just like type in the chat. Either way. How do you get the numerator? Okay. So the numerator is probability of A intersect B union C. So I'm going to look at A intersecting with B union C. So B union C is everything here in red from our Venn diagram. So our Venn diagram would be everything in red for B union C. Now I have to figure out where does A intersect B union C? Well, A intersected with B union C is everything here in green. So everything in green added together is 0.12. So A intersect B union C is in green. So it's going to be 0.03 plus 0.05 plus 0.04, which is 0.12. So let me know if that's helpful. Okay. Cool, cool. Other than the given hint, how did you know to do B and C before A and B? Oh, that's a good question. Okay, so that's a notation issue, really. So the notation here, it's like this is one event. I see. Good question. So notationally, we do right-hand side of the bar before the left. Good question. Oh man, that's crazy. Unstable internet. I guess because we have 11,000 people online right now. Let's see. I guess we could say that this is not a set operation. So this wouldn't make sense to do this first. So this is not a set operation. It's a probability operation. So there's no way for me to combine A and B using the vertical bar and then union that with C. That's not a set thing. That's something we use with probability. I don't know if that, does that make sense, Branson? Okay, sweet. Good question. All right, cool. Good example. Now, part C, what's the probability of A union B given C? So that's going to be probability of A union B intersects C. Have to be careful. Over probability of C. So probability of A union B intersects C. And we go back up to the Venn diagram. And let me erase some of the stuff here. So now let's do, we are trying to look at A union B, which I'll color in green. A union B. And now intersect that with C. So intersection with C just produces this right here. So I'm going to add these two together, 0.05, 0.04, so that's 1.17. So that's going to be equal to 0.17 divided by probability of C, and that was given as 0.37. And punch that in. Let's see, calculate here. 0.17 over 0.37. And that's 0.4595, we'll round, or we'll say 0.45946. we'll round it there. So let me just draw the diagram. Kind of highlight what the pink part is. The pink part is right here. A union B intersected with C is right here. So you go back to the original diagram that has all the numbers in it, add those three, and then divide by the total C probability. And C is here. Probability of A union B union C. So A given A union B union C. So that's going to be probability of A intersected with A union B union C over probability of A union B union C. So A intersected with A union B union C should just be A. So if you think about that, we got A, B, and C. Then all three would basically be the green. And then intersect A with that, you just get A again. So if you just intersect A here, you just get A again. So that's interesting that A equals A intersected with A union B union C. And then divided by probability of A union B union C. Again, probability of A was given in the problem, which is 0.14. Probability of A union B union C is everything that's inside. So basically 1 minus this number right here. So 1 minus 0.51, which is 0.14 divided by 0.49, which is 0.286, we'll say. 0.286. Again, any questions in the chat? Or if you just want to turn on your microphone, maybe feel free to do that too. This is being recorded. If you don't want to be recorded, just leave the screen share and then go watch it later. So I forgot to mention that at the beginning. Okay, if there are no questions, we'll keep going. See what else we can do. The multiplication principle for conditional probability, it basically just does a little algebra to our original formula. So if you go to our original formula, way up here, there it is, and you multiply by probability of B, you can get the intersection by itself. And then same thing, you could do the same thing here, multiply by probability of A and get the intersection by itself again. So that's really all they're doing, is just a little algebra to these two formulas up here that we have. And they get a formula that they call the multiplication rule for conditional probability or for the intersection. So basically probability of A intersect B is probability of A given B times probability of B. And it's also equal to probability of B given A times probability of A. So it's just algebra that they did. It's useful whenever you have like events that are in succession. So when you start to get multiple events, not just 2, but maybe 3, 4, however many events, it can be really useful to rewrite your conditional probabilities or rewrite your intersections as conditional probabilities. So basically this would be probability of A1 intersect A2 intersect A3. you could rewrite that as probability of A3 given A2 intersect A1. Well, that is probability of A2 intersect A1 is probability of A2 given A1 times probability of A1. So if A1 occurs first, you can find this probability if you know these conditional probabilities, which you generally do. You know what percentage of people have the disease given that they tested negatively for it. All right, so let's see, in 2.4, conditional probability Bayes theorem. This is where we're going to spend a little bit of time. These examples get pretty intense, so let's really break down what's going on before we get there. So the law of total probability uses what we call exhaustive events. Exhaustive events means that their union is the whole sample space. So the whole sample space can be written as A1 union A2 union AK, but we use a finite number of exhaustive events. I think that's standard and to use a finite number of events. So basically you could think of like exhaustive events like this box down here. You can see that A1 union A2 union A3 union A4 gives you the whole sample space. These are actually mutually exclusive events in that A1 does not intersect A2, A2 does not intersect A3, A3 is this crazy thing here, and A3 does not intersect A4, A4 does not intersect any of the other two, so they're all mutually exclusive. So pairwise disjoint is another word for that. So you might see this term pairwise disjoint. No two have an intersection. So then the probability of B can be written as, well, the part of B that intersects A3 plus the part of B that intersects A1 plus the part of B that intersects A2 plus the probability of the part of B that intersects A4. So you add all those intersections together and then just use use the conditional probability multiplication rule. To go backwards, to rewrite like this. This is called the law of total probability. To get the total probability of B, you find the probability of B given A1 times probability of A1 plus probability of B given A2 times probability of A2 plus ... probability of B given AK times probability of AK. And really to show this formula derived, you would just start with this. You'd say the probability of B is really just the probability of these intersections added together because all of these intersections are disjoint. So this is B intersect A1, disjoint from all the other intersections of B. This is B intersect A2. This is B intersect A3. This is B intersect A4. And we can just add them all together if they are disjoint. And that's our axiom of probability we started out with. So let's look at an example. It says I have 3 email accounts. If you're a tech student, you have at least 3 email accounts. The example says 70% of my emails come to account 1. We'll say A1. 1% of the emails in A1 are spam. So that's already a conditional probability. So this is probability. This is already a conditional. So that's, given that it's in A1, the probability of it being spam is 1%. So 70% go to A1, and then given that you're in A1, 1% of those are spam, you can guarantee. So what is the probability of B? Basically, what is the probability of me getting a spam email in any of my accounts? Well, that's going to be the probability of B given A1 times probability of A1 plus probability of B given A2 times probability of A2 plus the probability of B given A3 times probability of A3. Now, this 1% is the probability of spam given A1. And this 70% is probability of A1 because 70% of my emails go to account 1. So you already have the information, you just have to pick it out correctly from the text. This right here is probability of A2. This is going to be probability of spam given A2. So probability of B given A2. And you get the idea. So what's going to happen is we're going to get probability of B given A1 is 0.01 times 0.7 plus B given A2 is 0.02 times 0.2 plus 0.05 times 0.1, which is going to be 1.6 or 0.016. So about 1.6% of the emails that I get are spam. So about 1.6% of my email is spam. So that's a good example to look at. I like that one. Just introduce this idea of total probability. So again, any questions? Just check the chat, or you can, unmute your microphone, and we'll stop for a second. So cool. Now, Bayes' theorem. So Bayes' theorem, basically we have the same setup as the law of total probability, and we just use the denominator, basically the conditional probability definition. We just replace the denominator with the law of total probability, and that's Bayes' theorem. So this equality is by the law of total probability. This is just by definition. Right, that would just be the definition of the conditional probability AJ intersect B over probability of B. The only thing that changes is if we use the total law or the law of total probability in the denominator, then we get to rewrite our probability using that summation. So pretty intense looking, at least. Once you get the hang of it, it just requires a lot of practice, honestly. Like the hard part is looking at the word problem, figuring out what's given, are they conditional probabilities, are they intersections, and just trying to piece everything together. So hopefully this example here will help that come to light, because it's pretty intense, and it's one that's it's kind of strange actually. It makes sense for the most part until we get to the final answer. But it says a rare disease example, 1 in 1,000 people have the exploding head syndrome. Hopefully that's fewer than one. But a company has developed a diagnostic test. We know that if an individual has the syndrome, a positive result on the test has probability of 99%. So given that you have it, we can pretty much know if you do. So we know that if an individual has a syndrome, then the result on the test is 99%. Like we can know 99% of the time that you do have it. If the individual does not have the syndrome, a positive result has a probability of 2%. So what is the probability of someone having the syndrome if the results are positive? Basically, you don't know if you have it. You want to be tested for it. What is the probability that you have it? So let's see. quite a lot to take in here. They're going to define some events here. A1, it says probably A1, or sorry, event A1 is the event that an individual has the syndrome. So what is the probability of A1? We should be able to get that. Well, probability of A1 is 1 out of 1,000, right? 1 out of 1,000 people do have the probability. So that's our probability of A1 by itself. And then A2 is A1 complement. So probability of A2 is going to be 1 minus probability of A1, which is going to be 1 minus 1 over 1,000, which is going to be 999 over 1,000. Again, I recommend just using fractions instead of decimals. It's going to be easier. The diagnostic test gave a positive result. Let's see. So what do we know? We know that if A1, so probability of B given A1 is 0.99, or you could say 99 over 100. So 99 over 100. So that is the first one. It says, if we know that an individual has a syndrome, a positive result on the test has a probability of 0.99 or 99%. So that's the probability of a positive test result given that they have the syndrome. So 99% of the time we can correctly identify or give a positive result if the person, if we already know the person has the syndrome. So let's see, probability of B given A2 is going to be, let's see, what's the positive result probability given that the person does not have a syndrome? That's 0.02 or 2 over 100. Again, I guess we could use decimals here since they don't repeat. So these are all our decimal answers. So probability of B given A2 is 0.02. Because it says a positive test result given that the person does not have the syndrome. Now, probability that someone has the syndrome if or given that the test results were positive. So that's A1 given B. What's the probability that someone has the syndrome given a positive test result? So, well, that is going to be probability of A1 intersect B over probability of B. So basically, Bayes' theorem says, okay, flip it and say probability of B given A1 times probability of A. So basically, A1, basically use the multiplication principle in the numerator. And then in the denominator, put that one again, using the law of total probability, plus, and then throw in B given A2 times probability of A2. So that is going to be our answer. And that's going to be, let's see, fill in all the pieces, 0.99 times 0.001 over 0.99 times 0.001 plus probability 0.02 times 0.999. So whatever that turns out to be, it's going to be like 0.0472, which is about 5% of the time. That's awful. If this thing's supposed to tell you when you actually have the disease, if you have a positive test result, it's only correct 5% of the time. Meaning, given that you had a positive test result, you're really not going to know whether or not you have the disease. So this is not a very useful test for identifying the disease. It is useful if you already know whether or not you have it, which is really strange. So, but anyway, these Bayes' theorem problems are pretty interesting. They always take a lot more thinking than just a standard problem. So really dive in, really try to understand this example to start off and see what else we can do from there. So again, any questions? I know that one's a lot, but just knowing what you're given is the key. So it's kind of the wording kind of tells you, we know that if an individual has a syndrome, a positive test result, it's basically probability of a positive test result given that the individual has a syndrome. Basically, if this occurs, then this occurs. This is basically your second part, the part that you're looking at after this occurring. So that's the heart of conditional probability. All right, so now independence 2.5, not related to July 4th. Two events are independent if probability of A given B is still just probability of A. So B occurring has no change. It is not affecting the occurrence of A. So it does not change the sample space at all, basically. So otherwise, they are dependent. So if these two are not equal. So if they are independent, then what can we say? Well, we know probability of B given A by definition. So again, this is just by definition. Probability of B given A is just probability of B intersect A over probability of A. Well, I can use the multiplication rule to rewrite the numerator. And now what do I know? I know that this probability is unchanged by B, meaning it's just probability of A. So this probability is unchanged by the fact that B has occurred. So this is just probability of A. So then the probability of A cancels, and that's just probability of B. So if A is independent of B, then we can basically say that B is also independent of A. That's all this says. It just says B is also independent of A. The complements would also be independent since the original events are independent. We're not going to go through any proof there. If A and B are disjoint, then probability of A intersect B, would be 0. Probability of A given B, though, would also be 0 because A intersect B would be 0 because it's the empty set, because they're disjoint. So see, they would then be dependent, assuming that A and B are not the empty sets themselves. So the probability would change. So they're definitely dependent. Also, if A and B are independent, then probability of A intersect B equals probability of A times probability of B, because this one, we said, doesn't change if B already occurs. So it's just probability of A. So basically this thing right here is just probability of A because it's unchanged, because it's independent of B. B does not change that probability. All right, so I think these in example A here, if you have if you roll 2 dice, or if you roll a die and then roll it again, you have 2 dice rolls. Then let's say A is a probability you get a 1 on the first roll, B is the event that you get a 5 on the second roll. I think those should be independent, right? You shouldn't expect to get a 5 or not get a 5 on the next roll, given that you got a 1 on the last roll. That's silly, right? It's unaffected. The die doesn't remember what it got last time, and it doesn't know that it should change itself. It's just going to be whatever it is, 1 out of 6 regardless. So part B, a car has a 4-cylinder engine is event A, and event B is a different car has a 6-cylinder engine. It's like the cars they're completely independent of each other. Like the fact that you put a 6-cylinder engine in one car, it's irrelevant compared to another car. So it's just independence of events. They're not affected by each other. Unlike lung cancer and smoking, I guess you could say, like they should not be independent if we just think about it. Like if you say, what's the probability of having lung cancer, well, it's like, whatever it is, pretty small. But given that you're a smoker, what's the probability of having lung cancer? It probably goes up quite a bit. So it's definitely not independent of smoking. So lung cancer is probably not independent of smoking. So that's kind of the idea, is independence versus dependence. So I would say that lung cancer is definitely dependent on smoking. If you smoke, you're going to have a higher chance it's going to go up. So the probability is going to change. So if you have more than 2 events, it's pretty nice, because that thing we mentioned earlier with writing the conditional probabilities just breaks down into a bunch of multiplications. So if you have a bunch of mutually independent events, then the probability of their intersection is just the multiplication of the individual probabilities. So we're going to see that here in an example. So consider the following system of 2 subsystems, subsystem 1, 2, 3, and then subsystem 4, 5, 6. Assume that for the system to work, at least one of the 2 subsystems should work. So that means this one should work, or this one should work. Assume that each individual component functions with the same probability of 0.9. So this component has a 0.9 probability of working, this one has a 0.9, and basically each component here has a 0.9 probability of working. Assume the individual components themselves are independent. What is the probability that the entire system works? So the probability that the entire system works is basically like 1 union 2 union 3, or sorry, intersect 3, because they have to all be working at the same time. That's basically an and. So A1 intersect A2 intersect A3. So probability of this component working versus probability of this component working. Probability of A4 intersect A5 intersect A6. So I need at least one of those to work, which means I stick a union between them. So A1 intersect A2 intersect A3, or A4 intersect A5 intersect A6. If either one of these components works, so this is top component, this is bottom component. If either one works, then we're good to go. Now, what do we need to do? We need to say, okay, probability of a union, so don't forget, probability of a union, we'll call it C union D, was probability of C plus probability of D minus probability of C intersect D. So basically this is C and this is D, and I just want to look at the probability of C plus probability of D minus probability of, this is basically like C intersected with D. So if you want to treat C as A1 union, or sorry, intersect A2 intersect A3, and D as A4 intersect A5 intersect A6. This is basically like probability of C plus probability of D minus probability of C intersect D. Now, because they're independent, this is really just probability of A1 times probability of A2 times probability of A3 plus probability of A4 times probability of A5 times probability of A6 minus probability A1 times probability A2, because they're all independent. So you can just multiply P cubed plus P cubed minus P to the 6th. And it says the probability of each individual component working is 0.9. So that number comes out to be 0.927. If you only had one subsystem, the probability would be 0.73. So actually there's a better chance of, the thing functioning if you have 2 subsystems. So basically that to say, is it worth the cost? If I function 92% of the time, or 93% of the time versus only 73% of the time. So you get 20% more time to function, or production time. I think we'll just stop here. We'll work this next example next time, maybe come in with some questions. Um, I don't want to just keep going necessarily. We're kind of almost through with chapter 2, and I still plan to cover some chapter 2 stuff next time. So on my schedule. So let's slow down a little bit. I'm sure I'm going way faster than I normally would in class because you guys aren't like very vocal. So yeah, we'll just stop here. Maybe look at this example, try it out on your own. I'll work it next time. Also start working on the web work for this chapter, like start working on these problems, and you can ask questions about these problems next time. We may have like a little discussion, just working through some web work problems if you guys have questions, or maybe if you look at some book problems and you want to go through those as well. So any questions before we wrap up here? I'll just check out the chats again. If you want to just turn on your microphone, that's fine too.
For practice problems, do you recommend just using the book?
Yeah, I mean, for the exam, that's usually where I pull problems from, is like the textbook. So they're really a lot better, I think, than web work, because web work, you just have a different mindset for working problems, because you're like, okay, I'll just try this answer, and then, if it's wrong, I'll just try it again, or I'll try something else or whatever. But if you do a book problem, it's more like an exam, because you're just like, I have no idea if I'm going to get it right or wrong. And so it just kind of simulates that test environment a little more. But yeah, both will be,
Okay.
Yeah. So, okay.
Dr. Walters, would you be willing to post all of the chapter slides on Moodle so I can just go to the print station and print it once instead of having to go multiple times?
Oh, yeah, I gotcha. I'm really trying to like dig through with a fine tooth comb, make sure I've got all the errors out of these things. So I'm pretty sure I do, but I'm taking my time this time around to make sure that I have all the errors, because I've had errors in the past. So if I post them, they may have errors, but I think I've got them all out actually. So I'll just go ahead and post them. If they have errors, I'll just fix it on the fly, and you can fix it as well. So yeah, maybe so. Maybe I'll just do that.
Okay, sounds good. Thank you.
Yeah.
Do you have any news on like how we'll test yet?
There are a few ideas, but nothing concrete, nothing solidified yet. There have been talk of like creating our own tests through some open courseware. We've thought about sending you to proctors, although that's less likely to happen because you weren't prepared for an online class. Like normally for an online class, we just have you guys like go to a proctor at a testing center somewhere. You pay $20 or $25 or whatever per test. But that's like an added expense you weren't prepared for with this because you weren't expecting an online class. So yeah, so I probably won't send you to a proctor. I may proctor you like live, like you may have to turn on your webcam and work an exam, right there, and have your microphone on and everything. So we haven't nailed it down yet, but once we get it nailed down, we'll let you know. And yeah, so I generally, in my class, this is already like open book, open notes, so I'm not worried about that. So yeah, the questions are typically a little harder and, more tedious because you have those resources already. All it really is important for is like knowing where the formulas are, So if you know where the formulas are, you can thumb through them pretty quickly, like look through the slides or look in your book or whatever. So, but yeah. I'll let you know as soon as I know. We're still brainstorming different ways to do it. Other questions? Again, I'll share a link to this video as soon as this is done on the Zoom cloud processing or whatever. So there are no other questions. I'll see you guys or talk to you again on Wednesday. Again, if you want to use office hours, I'm going to post a link on Moodle to a Zoom office hours meeting, and you can use that if you're if you don't want to come up here, but you're still free to like stop by my office. Again, I recommend, especially now, actually, I recommend scheduling office hours through my Google Calendar. I sent the link on the syllabus already. So if you need to schedule office hours, use that for sure. That way I'll know, who's planning to meet with me or whatever on Zoom, especially. So anyway, I guess I'll talk to you guys later. Have a good one.